Hello everybody, this is Professor Roman. Welcome to the fourth video in my lecture series, An Introduction to Discrete Mathematics. We're ready now to discuss one-to-one correspondences. Now that we have some familiarity with the basic concepts of set theory, I want to consider the following two questions. What does it mean to say that a set is finite or infinite? And what does it mean to say that two sets have the same size? Now, you probably already have a sense of how to answer these two questions, but let's remember that we need to formulate very precise, careful definitions for these concepts in the hopes of avoiding any future unpleasantness in the way of contradictions. So we need formal definitions. It turns out that in order to answer the first question, we need to answer the second question first. So let's address that question. Here are two sets, for example. What we need is a direct way to decide whether these two sets have the same size or not. Now, you may be saying to yourself, well, obviously they do. Each one has 5 elements. But that's cheating because we don't know how to count elements yet. I'm going to talk about that a little later. So right now we're staring at two sets and we see their elements. So a direct method for comparing these two sets to see if they have the same size is simply to pair the elements in the two sets. One element of the set A with one element of the set B. Being careful to use each element exactly once, each element in the two sets. So the M that lies in A should be used exactly once on one side of the pairing, on the A side, and the element M in the set B should be used exactly once on the B side of the pairing. If we can do that and run out of elements in both sets at the same time, then we have what I will refer to as a complete pairing. That's not a standard term, so you probably won't see it elsewhere, but it's convenient for us. Here is an example of a complete pairing. A is paired with 7, C with 6, J with A, and so on. M happens to be paired with itself. You can scramble the elements on one side, like the B side, and still have a complete pairing as long as you don't duplicate any elements or remove any elements. So, if a complete pairing exists, it seems, at least in this case, and probably you can stretch your imagination to any pair of finite sets, that a complete pairing should be a good definition for two sets to have the same size. The nice thing about looking at a pairing is it doesn't involve anything outside of the two sets. In particular, it doesn't involve the set of natural numbers or counting numbers. These two sets, C and D, do not have a complete pairing. Intuitively speaking, it's pretty obvious, no matter how you try to pair the elements, never using an element more than once, you're going to run out of the elements of D before you've used all the elements in C. Now, strictly speaking, we should come up with a proof, even though it seems quite obvious, and I will do so later on, okay, in a little bit more indirect manner. And also, I get the feeling some of you may be thinking this is a little bit pointless, maybe even a little bit silly, because all this is so obvious. But stay tuned to this channel, because when we discuss pairings of infinite sets later in the chapter and in a later video, the whole thing is going to become much more meaningful, and it's going to lead to some consequences that may at first seem, let's say, questionable, but turn out not to be. This is where we get into the fascinating story of Cantor's development of infinite sets and their sizes. So I'm approaching this slowly, the basic concept of a complete pairing in terms of simple finite, small finite sets. But if that was the end of the story, I wouldn't be doing this. Now, the notion of a complete pairing, the way I've just described it, is informal, and we should be more precise, and that's easy to do, because a complete pairing of the elements of two arbitrary sets, say A and B, is just a bijection from A to B, or from B to A. It doesn't matter. If we have a bijection going in one direction, we have a bijection going in the other direction. We just take the inverse. So I can speak in terms of bijections from A to B, or bijections between A and B. So if there is a bijection between two sets, we will say that those sets have the same size. But I'll still use the term complete pairing once in a while, and I might write a pairing like this as I did before. What this means, if the bijection is denoted by F, this means this, that F of A is equal to B. In the context we're talking about here of comparing set sizes, bijections are almost always called one-to-one correspondences. Okay, but the two concepts are the same, just different terminology. So we're now ready for a definition. Two sets A and B have the same size, and that now for us is a technical term, same size. Other terms are equipolant, equipotent, and equinumerous. If there is a one-to-one correspondence, or in other words, a bijection, from A to B, or between A and B. But if the bijection is F from A to B, then we would write this. I will write this. This notation, this approximate symbol, I've seen it in other places. I don't know that I would say it's universal, but it is relatively common. Okay. If we don't care about the specific bijection, if all we care about is that there is a bijection, then I would just write either this or this. And again, for emphasis, this is the definition, universally accepted definition for what it means for two sets to have the same size. Okay? And a phrase like two sets have the same size if they have the same number of elements is not precise, and you should avoid it, at least in a mathematical context. It's not too bad for finite sets, but you still have to explain what you mean by the number of elements in a set, but it's kind of fatal for infinite sets. Just as somewhat of an aside, if you have two arbitrary sets and you write them in indexed notation, then we can show, or we can describe the fact that these two sets have the same size, either by using the definition and finding a bijection from A to B or from B to A, or we can define a bijection between the index sets instead. And that's because an index uniquely determines the element and vice versa. So an index or the element itself are just two ways of describing the same thing. Examples. The pairing that I discussed in the first video when I was talking about how faulty our human intuition can be in the setting of mathematics. This was a pairing of the natural numbers and the even natural numbers. So this is a one-to-one correspondence in official language, and here is a bijection or one-to-one correspondence. This is its inverse, equally good. There's an important one-to-one correspondence between the power set of a set of size n and the set sigma sub n of binary words of length n. And to illustrate this one-to-one correspondence, let's take an example of this set here. It does have 5 elements, but that's sort of an issue we have to deal with later. We can pair a subset T of S with a binary word of length 5 that has a 1 in the ith position if and only if the element A sub I belongs to the subset T. So in this case, some examples are worth 1,000 words. In fact, let's just look at this third one. The subset T contains A1, A3, and A5, so we put a 1 in the first, third, and fifth place, and zeros elsewhere. So whenever you look at this binary word, you know immediately which elements are in the subset. In this case, it's the entire set. In this case, it's only the first element, A1. Here, it's only A2 and A3. And I'm going to leave it for you to, if you wish, to construct what you consider a convincing argument that this really is a one-to-one correspondence. And this will work in general, that if a set has the same size as z sub n for some particular n, then its power set has the same size as the size of sigma sub n. Here's another example. If sigma and omega are finite alphabets of the same size, then these two sets, sigma star and omega star, all the words over those alphabets also have the same size. As a matter of fact, any one-to-one correspondence between the alphabets, sigma and omega, can easily be extended to a one-to-one correspondence between sigma star and omega star. So again, let's look at that by example. Here's sigma and here's omega, and here is a one-to-one correspondence, kind of the obvious one. To extend this to a one-to-one correspondence between words over sigma and words over omega, we just apply this one-to-one correspondence to each letter in the word. The words have the same length. So for example, for this one-to-one correspondence between the letters, the word 2-1 corresponds to BA, because 2 corresponds to B and 1 corresponds to A. It's quite simple. 4-3-1, just track it down, D, C, A. Okay? So if sigma and omega have the same size, then so do sigma star and omega star. Much bigger than sigma or omega, of course. This is an example for finite sets, and I'm going to leave it for you to ponder, does this work equally well for infinite sets? There is a very useful property of one-to-one correspondences that we will find handy a couple of times when we look at some proofs coming up. And it goes as follows. Suppose that F is a one-to-one correspondence or bijection from A to B. And these are the sets written in index notation. And suppose that two of the pairings in this correspondence are AI paired with BJ and AK paired with BL. So this is an arbitrary couple of pairings. And suppose also that we don't like this particular pairing for some, or set of pairings for some reason, as we will not like them in some upcoming proofs. We would rather that AI is paired with BL, so this one is paired with this one, and AK is paired with BJ. That's not a problem. We can change the original correspondence by swapping these two pairings and still have a one-to-one correspondence from A to B. I mean, after all, we still have the two required properties, injectivity and surjectivity. Now, if we were to change BL here to BJ, we would have two BJs here. We would lose injectivity, and it wouldn't be a one-to-one correspondence anymore. But swapping these two is not a problem in terms of being a one-to-one correspondence. Now we should look at this again a little more formally so we can use it effectively later on. The swap of BJ and BL is really just done by a bijection from B to itself that sends BJ to BL and BL to BJ and doesn't move the other elements in capital B, leaves it alone, leaves them alone. Then this composition is what we want. It swaps those two pairings and leaves all the other pairings alone. And the composition of two bijections is a bijection. I have to apologize. I should have mentioned that clearly in the previous video, and I didn't, so it's my fault. And it's something you should think about. You should be able to prove that. You should be able to prove that the inverse of a bijection is a bijection, and that the composition of two bijections is a bijection. Now, taking this more formal point of view, it's clear that G could be a more complicated bijection than just swapping two elements. Any bijection will work. You can apply any bijection to the B side of a one-to-one correspondence and still have a one-to-one correspondence. Or you could apply it to the A side. That would be taking a composition in the reverse way here, where G was a bijection on A instead of B. There's no reason to swap both sides. You have to do it one at a time, because you can accomplish that by swapping one side only. But sometimes it's more practical to think in terms of swapping the A side, applying a bijection to the A side, then later on applying a bijection to the B side. And I'm going to do that, actually. So just for terminology, I'm going to refer to this application of a bijection as rearranging one side of a one-to-one correspondence. So rearranging one side of a one-to-one correspondence produces another one-to-one correspondence. Now we're in a position to define the term finite and infinite as it applies to sets. But let's start by asking a question. How do we really count the elements in a set? Well, the answer is quite simple. Here is a set. How do you count these elements? You would go 1, 2, 3, 4, 5. So you will pair the elements of the set A with, in this case, the elements of the set Z sub 5. And here is one such pairing. I could have counted differently. 1, 2, 3, 4, 5. It doesn't matter. That amounts to a rearranging of one side of this pairing. But most people will count from left to right or from right to left. So this is precisely finding a specific bijection from A to Z5. And more generally, counting the number of elements in any non-empty set would amount to finding, if it's possible, a one-to-one correspondence between the set A and a set of the form Z sub n for some positive integer n. And if we can do that, then we can say that the set is both finite and has n elements. So that could be written this way. This is just simply saying that there's a one-to-one correspondence between A and Zn. This is more explicit in saying that, that the set A has n elements or has size n. It shouldn't come as a surprise that we cannot count the number of elements in the set of all natural numbers. But that's something that also requires proof, and I will do that later in the book. But now we have an official definition of finite and infinite. So let A be a non-empty set. If A is empty, by the way, I'll say it now, it's by definition finite, and by definition has 0 elements. But if A is non-empty, if A is in one-to-one correspondence with one of these sets, Zn, then we say that A is finite and A has n elements or has size n or has cardinality n. And write this. If A is not in one-to-one correspondence with any of these sets, or put another way, if A is not finite, then we say it's infinite, and we can write this. Now we're going to refine this considerably. This just simply says there's no one-to-one correspondence between A and a set Zn for any n. Turns out, as Cantor first discovered, that infinite sets can have many different sizes, and we'll be able to put something here, that some exotic symbols that actually measure, in a sense, the number of elements in an infinite set. Well, now, do you know, oops, I got to move that down. Do you notice a problem with this definition? There is a problem, and I would encourage you to stop the video and give it some thought. See if you can spot the problem. It is a bit subtle, but it's serious, very serious. How do we know that a set A cannot be in one-to-one correspondence with two different sets, Zn and Zm, where n and m are different. If that could happen for some exotic set we've never seen before, then the concept that we are defining here is not well defined. It's ambiguous. If there are two bijections here, one f from a to zn and one g from a to zm, we got a problem. So I think you would agree that's not going to happen, but we have to write down a proof just to be safe. And fortunately, it's quite easy. If we have these two bijections, then this composition, F inverse followed by G, F inverse will take Zn to A, G will take A to Zm, so we go from Zn to Zm, is a bijection. Because F inverse is a bijection and the composition is a bijection. So now we are presented with a bijection or one-to-one correspondence between Zn and Zm directly. A is now out of the picture. And we can assume that n is less than m, because if it's not, we can just swap the roles of n and m. All we need to do now is show that this is impossible. And maybe I shouldn't say all we need to do, because there's a little work here. There's an idea here that's necessary. First, rearrange, if necessary, the Zn side so that those elements appear in order. And quite frankly, you have the right to ask me, what do you mean by order? Because we haven't discussed that. But we'll stretch a point here and say that the order is 0 followed by 1 followed by 2 and so on up to n. Then we do the same thing on the Zm side. We still have a one-to-one correspondence. And the first n pairings, or the pairings from 0 to n, look like this. 0 pairs with 0, 1 with 1, and so on up to n with n. Now we see what the problem is. Zm contains the natural number n plus 1, the next natural number after n. But there's nothing on the Zn side to pair it with. So we ran out of the Zn elements before we exhausted the Zm elements. And again, all this now should seem pretty obvious. But we have here a convincing formal argument. Okay. The only way out of this contradiction is to admit that there is no one-to-one correspondence from Zn to Zm, because that leads to this problem, this contradiction. Now we can say that this definition is rock solid. Okay? We've eliminated this problem. And I hope you can see that this is something we needed to do. Okay? Something that could have easily been overlooked if we weren't being, really scrupulous here. Sorry for these interruptions. Unfortunately, I can't move those notifications to another monitor, at least not easily. Okay, so as a result of this definition, which we now know is contradiction-free, at least we hope is contradiction-free, if A is a finite set, then A is equipolant to Zn for some n, And so we can index A by using Zn as an index set if we want. And so this is one way to write it. So is this. Oops. Not too good at this. There we go. As I mentioned, the set of natural numbers is infinite. We can't count the number of elements in the set. It's not in one-to-one correspondence with any z sub n. But we haven't proved that, and that's something we need to do. And as I mentioned before, we will do it. One way is to use mathematical induction, and since I haven't discussed that yet, we'll have to wait. In general, it's not always easy to tell whether a given set is finite or infinite. In fact, remember Fermat's last theorem that we discussed. Fermat said the set of exponents greater than 2 for which there's a solution to the equation x to the n plus y to the n equals z to the n is empty. And it took 350 years for us, from the mathematical community, to actually prove that. So for that 350 years, nobody knew whether that set was finite or infinite or empty in particular. So that brings us to a result here that's fairly modest, but actually a lot more useful than it might appear. If A is a finite set, then any subset of A is also finite. That's something you would expect, and it feels intuitively accurate. But, as always, we need a proof. If A is an infinite set, then any superset of A is also infinite. That follows from part 1 in just a line or two. So let's address part 1. So A is a finite set, which means we're allowed to write it like this for some positive integer n. If A is the empty set, then there's only one subset itself, so we don't have to worry about that. But in any case, this is what, in the other case, this is what A would look like. And let S be a subset of A. If S itself is empty, then it's finite by definition. There's nothing we need to do. So we can assume S is non-empty. And suppose there is a one-to-one correspondence from A to Zn. In other words, A has size n. And notice the way I have written this. It would have been easier just to write A1 is paired with 1, A2 with 2, and so on. But I wanted to be more general. So I am double subscripting A sub I sub 1, A sub I sub 2, A sub I sub 3. So I1, I2, I3 up to In are natural numbers in any order. I remember, just as an aside, the first time I taught a transition course, I hadn't written my own book at that point, so I collected a bunch of books, textbooks on the subject, and also some of these books had a chapter on mathematical style, and several of them said, never use double subscripts. I don't agree with that. I think sometimes, in some points, they're important to use. Some students will tend to freak out by it, but if you just take it slowly, I don't want to put a subscript 1 here and 2 here and 3 here. I want to put arbitrary subscripts. Subscripts are natural numbers, and so I have indexed the subscripts. I1, I2, and I3. Okay. Anyway, the elements on the right side here, on the Zn side, are in order. Okay. If they weren't in order for a particular correspondence, I rearrange it. Okay. And then I don't have to change the left side, because the double subscripting notation still works. Now we can reorder the A side, the left side here, so that the elements of the subset S come first. And I don't care in what order they come. Well, rather than try to invent a good notation for that, I could do it, but it's going to look kind of ugly, and I'm going to stop with the double subscripting. So what I just wrote here is element of S, some element of S, pairs with 1, some other element of S pairs with 2, and so on. The elements of S now come first. I don't think I can outline, no, I can't outline just a handful of these, but the first group here up to this line are the pairing of the elements of S with the natural numbers. The rest are elements of A that are not in S. This is still a one-to-one correspondence. Well, if K is the integer on the right that matches with the last element of S, then we could throw out the rest of the pairings, and we would have a one-to-one correspondence between S and Z sub K, telling us that S is both finite and has size K. And that proves part 1. And I'm going to leave you to think about how part 2 follows from part 1. It's 3 lines here. Okay. Let's have an example. Since the set n of natural numbers is infinite, which is proof pending, it follows from part 2 of the theorem we just discussed that the supersets, Z, integers, Q, rationals, R, reals, are all infinite sets. The point here is that we don't have to show that there's no one-to-one correspondence between, say, Q and some Zn, or R and some Zn. We don't have to write anything down. All we have to say is that n is infinite, therefore so are all these other sets. So it's a great savings of effort, really. Okay, let's conclude this video lecture with 1 to K correspondences. One-to-one correspondences, as we've just seen, I hope, are extremely important. But there is a generalization that will be important for us as we explore the subject of counting, which is going to occupy a considerable portion of this course. As we've just seen, a one-to-one correspondence matches each element of a set A with a unique element of a set B. Or we could say it matches an element of A with a unique singleton subset of B. And equally important for counting purposes is a correspondence that maps each element of A to a unique subset of B of a fixed size K. So all the subsets matching with the elements of A have the same size K. And here's a formal definition. Let A and B be finite sets, and let K be a positive integer. A pairing that associates to each element, little a, in the set capital A, a subset, script B sub A, of B of size K, and for which the subsets together form a partition of B is called a 1-2K correspondence from A to B. So this is partitioning the set B into blocks of the same size, each block being matched with an element of A. So you can think of it as the blocks of the partition are labeled by the elements of A. One-to-one correspondences are bidirectional. If there's a one-to-one correspondence between two sets A and B, the two sets play a symmetric role, so we can think of it as going from A to B or from B to A. But with a 1-to-K correspondence, we have to be very careful. When K is greater than 1, we have to be very careful to identify the one side and the K side. Because if you swap the other way, it's not a 1-to-K correspondence, it's a K to 1 correspondence. Okay. Now here's the main point of this, the counting rule. If A and B are finite sets, and there's a 1-to-K correspondence from A to B, then the size of B is K times the size of A. If K is 1, we have a 1-to-1 correspondence. The two sets have the same size. And I'm going to refer to this as the 1-to-K counting rule. So here's a simple example. This is the set A, this is the set B. Here is a 1-to-2 pairing. Each element of A is paired with a doubleton subset of B, and these three subsets form a partition of B. So, in this case, the size of B is twice the size of A, which is rather obvious. As far as the counting of sets the sizes of finite sets is concerned, if we can find a 1-to-K pairing between the sets A and B in either direction, 1-to-K or K to 1, then the size of one set determines the size of the other, either by multiplying by K or by dividing by K. In fact, most people, I think, use this 1-to-K counting rule without even giving it a second thought. So, for example, if there are 30 students in each of 5 rooms, there are 150 students. Okay. This is an application of the 1-to-30 counting rule. In each of the one side are the 5 rooms. Each one is matched with or paired with a group of 30 students. So you multiply the size on the one side, namely 5, by the size of the blocks, 30. Okay. Well, up to now we've been concentrating on one-to-one correspondences between finite sets. And as I kind of alluded to earlier, the real interesting and important reason to do this is to be consistent when we turn to one-to-one correspondences between infinite sets. That's going to be much more interesting. And that's coming next. So thank you for watching my video. I hope you found it somewhat interesting, and I hope to see you in the next video.